Hi class, good morning. So again, this is the continuation of the topic in or the topics in thermodynamics 2. So by this time, we will now discuss the process of vapor. So this is somewhat like in an ideal gases. Okay. So in ideal gases, we have also processes like, say, for example, isothermal process, isobaric process, isentropic, polytropic, and so on and so forth. So by this time, so for vapors, so we have also the same processes. Okay? So let us now consider. So this is the general equation. So applicable to vapor. So this is similar to the steady flow energy equation. So where the tensile energy 1 plus kinetic energy 1, internal energy 1, floor work 1 plus Q is equals to P sub 2, or the potential energy at 2, kinetic energy at 2, U sub 2, WF2 plus W. Okay? So, we can only eliminate, or we can eliminate those properties or parameters who is not present. Okay, so in vapor. So, or simply, we have Q is equals to the change in internal energy plus the work non-flow. Okay, so for constant pressure process, so this is the first process involved in this vapor. So for constant pressure process, so we have here the process on PV and T is the planes. Okay, so getting the enthalpy of the vapor, that is equivalent to the enthalpy of the liquid plus the quality of the vapor multiplied by the enthalpy of the mixture. Okay, so or H equals to HF plus X HFG. So where X here now is the quality of the steam. Okay, so another condition we have here, the work of a reversible non-flow constant pressure process. Okay, so the work for the reversible non-flow, so we have here W sub n is equals to P integral of PdV. So which is very similar to the work non-flow in the ideal gases rather. Okay, so or simply P multiplied by the change in volume. Okay, so P multiplied by B sub 2 minus B sub 1. Or simply, for steady flow process, work steady flow is equals to the change in enthalpy minus the change in kinetic energy if present. Okay, so plus the heat transferred. Okay, so I think the equation is clear. Okay, so next, for letter C, we have for the heat transferred. So for simple energy equation, again, this is already presented. Q is equals to delta U plus work non-flow. Or simply, for steady flow, we eliminate the W sub n, or the work non-flow. Okay? So because this is only applicable to non-flow process. So by this time, for steady flow, Q, or the heat transferred, is equals to the change only of the enthalpies. Okay, so where, of course, for the enthalpy at 1, so that is equals to HF1, or the enthalpy of the liquid at condition 1, plus the quality, of course, of the steam at condition 1 multiplied by the mixture, or the enthalpy of the mixture, or H1 equals to HF1 plus X1 HFG sub 1. Okay? So, we have very short equation. Okay? So, very limited. Okay? So, let us now, so if the change in specific internal energy is desired, okay? So, that is equals to the change in internal energy is equals to the change in enthalpy, or H sub 2 minus P sub 2 B sub 2 minus H1 minus P sub 1 B sub 1. Okay, so I think this is more clear if we take up this example. Okay, So if you consider this. So let us now take this example. A piston cylinder containing steam at 700 kilopascal and 250 degrees Celsius undergoes a constant pressure process until the quality is 70%. Okay? Determine the per kilogram A, work done. B, the heat transferred. C, this is the change in internal energy. And D is the change in enthalpy. Okay, so before we can solve this problem class, we can first take a look at the values. Okay, so in the tables. Okay, so let us now consider that in the next slides. Okay, so we have here the given. The pressure is 700 kilopascal and the temperature is 250 degrees Celsius. Quality is 70. Required W, Q, delta U, and delta H. Okay? So, from table 3, so, vapor. So, at 0.7 megapascal. So, take note class, table 1 is for saturated temperature. Table 2 is saturated pressure. Table 3 is superheated table. Okay? And table 4 is compressed liquid. Okay? So, if you take a look now, the table 3 at 0.7 megapascal and 225 degrees. So, 250 rather, 250 degrees Celsius. So, the value now is B is 0.3363. So, this is kilogram per cubic meter. Then, internal energy at 1 is 2718.2. So, kilojoules per kilogram. And then, H of 1 is 2953.6. And the entropy is 7.1053 kilojoules per kilogram Kelvin. Okay? So, and then, from table 2 at 0.7, okay? So, we can now easily determine the liquid, okay? The amount of the condition of the liquid at this pressure. So, B sub F is equals to 1.1080. B sub G is 272.9. Okay? Specific volume of the gas, and the mixture is 0.271712. For the enthalpies, okay, so we have here H sub F is 697.22. H sub G is equal to 763.5. And the mixture is 266.3. So actually class, this HFG is equals only to the difference of HG and HF. Okay? So next is for the internal energy, that is 696.44. U sub G is 2572.5. And the difference of U sub G and U sub F is 1876.1. Okay? So, solving now the condition of the specific volume at 2. So, take note class that at 0.7 or 70% quality of steam, this is the final condition of the steam. Okay? So, computing now, the specific volume now is equals to 0.191362 per cubic meter per kilogram. So, same. U sub 2 is equals to U sub F plus X, U sub Fg. Substituting values now. U sub 2 is 2009.71 kilojoules per kilogram. And for enthalpies, the same process. H sub 2 is 2143.63. Okay, so take note class that if you determine the correct values of the enthalpies, entropies, internal energy, specific volume, you can easily compute the required class in this problem. Okay? So, next. So, for the change in internal energy, since the internal energy at the initial condition are already given and same as for the final condition, so we can now simply subtract the two values. Okay, so the change in internal energy now is equals to negative 708.49. Okay, so and the change in enthalpy is negative 809.97 kilojoules per kilogram. And for the heat transferred, that is equal also to change in delta, or change in H rather. So that is negative 809.97 kilojoules per kilogram. Okay? And for the W, or the work, so P is 700, and B sub 2 is already computed. Okay? 0.1913624 minus the original volume, specific volume rather, 0.3363. Therefore, work now is negative 101.456 32 kilojoules per kilogram. Okay, so I think it is now clear to everybody. Okay? Thank you very much, class. Okay.